All right, folks, this is the very beginning of Chapter 9. So in Chapter 9, we are going to be dealing with sequences and mostly series the entire time. And mostly sequences that go to, or series that go to infinity. But first, let's kind of define what a sequence is, just so that we are all comfortable on that. So sequence is just an ordered list of terms with specific values. So like, if I say a sub 1, that is the first term. And if I say it equals 8, then the first term is 8. I could give you the second term is 4. I could give you the third term is 2. And if I were to actually write this sequence out, you may see it listed as 8, 4, 2, so on, so forth, out forever. Right? So this is just listing them. Let's see. If I have a n, so like here, I have a subscript n. So this is my nth term. So really, n is like a variable for us. So if I want to find my first term, then I will put in 1 for n. If I want to find my second, then I'll put in 2 for n. Third, 3, fourth, 4, fifth, 5, so on and so forth, right? Same stuff that you guys were doing at the end of pre-cal. So if I want to find my first 5 terms here, it's not asking for anything special. You don't even need to show that much work. You have 3 times 1 over 1 plus 4. For your second term, you have 6 over 6. So really, truly, I'm not even going to list out this much. But that is how I will find them, right? I'm just plugging in 1, plugging in 2, so on and so forth. So if I put in 1, that's 3 over 5. If I put in 2, that is 6 over 6. Remember, you don't have to simplify. 3 is 9 over 7. 4 is 12 over 8. 5 is 15 over 9. Right, and as for the first 5 terms, I have given the first 5 terms. Reduce them if you want to, but it's whatever, you don't have to. All right, write the first 5 terms of the sequence given by the first term is 4. That's nice, cool, thanks. And a subscript k plus 1 is 2a sub k minus 6. So how would I find my second term? Well, you told me to plug in 2 for my second term, right? So if I put in k equals 2, that will get me to a subscript 3 is 2a sub 2 minus 6. So while that's all well and good, it gives a relationship between the second and third term, it doesn't allow me to actually find the second term. So let's kind of backtrack a little bit. This is called specifically a recursive sequence, where it uses previous terms, just like we saw, it's going to use the second term in order to find the third. So in order to find the second, I would essentially need to let k be 1, such that in order to find my second, I'm going to double the first and subtract 6. And for this recursive sequence, my pattern here is to essentially double my term and subtract 6 to get to my k plus 1 term, or my next term. So double 4 minus 6 would be 2. Double that minus 6 is negative 2. Double that minus 6 is negative 10. Double that minus 6 is negative 26. And that would be my first 5 terms of that sequence. Alrighty. So next we're going to get into factorials, kind of just beginning definitions. We're kind of just doing a bunch of random stuff that will help you moving forward. So with factorial, let's say I have 4 factorial. This should have been something that you did in geometry, but in case you don't remember, it is 4 times 3 times 2 times 1. It is all of the integers below it all the way down to 1. If you have 0 factorial, this is actually, factorials are used to like figure out the ways of doing things, so it deals with combinations and permutations and things like that. So essentially, if I have 0 things, there's only one way to order 0 things. It's just I don't have anything. So 0 factorial is 1. This is a fact that you need to remember. But factorial, so like if I have n factorial, this can be written as n times n minus 1. You're taking away an integer. You're taking away another. You're taking away another. All the way down until I get to times 1. All right, so with these ratio stuff, n factorial over n minus 3 factorial can be written as, well, let's rewrite the n minus 1, n minus 2, n minus 3, n minus 4, so on and so forth, right? And then that is divided by The bottom one is starting at n minus 3, and then I'm going to subtract 1 as I go down, so n minus 4, and so on and so forth. The nice thing here is that the n minus 3 times the n minus 4, all that junk below, is going to divide out. So I'm going to be left with n times n minus 1 times n minus 2. And that is how this will simplify. I don't necessarily need to see all of this work. You will not see it if I'm writing stuff on a test or a quiz. I am comfortable enough by now to just go from there straight to my answer. So there's not really much work to be shown on these things. All right, this one has two n's. Don't get freaked out by the two n's. The one on your denominator has more since it's going to plus 4. So I'm going to start writing out the bottom one first. So 2n plus 4 would be my first. And then I just need to subtract 1 each time. So 2n plus 3, 2n plus 2, 2n plus 1. And at this point, I know everything multiplied down will be divided by the numerator, since it starts at 2n plus 1 and goes down. So all of that will divide out. So I am left with, make sure you have the 1 on top, 2n plus 4, 2n plus 3, and 2n plus 2. All right, all that good stuff. Okay. So the next thing we're going to get into is the convergence or divergence of a sequence. So convergence just means that it will eventually go to some number. So go to a number. Divergence means it goes away from all known numbers. So this is going to go to like plus or minus infinity as we go out forever. If it converges, then we will be able to determine wherever it goes to. So with this, again, there's not going to be much work that you need to show me. They have already predefined this sequence as a sub n. But I'm going to say the limit as n approaches infinity. I'm just trying to figure out what are these going to as they get really, really, really big. So as they get really, really big, they're going out to infinity. So as this sequence goes to infinity, I'm thinking about putting infinity in n and seeing what happens. This a sub n should go to 8, because that would be like 8 plus 5 over infinity, which is just 8 plus 0. This one I'm going to want to do some simplification first. So notice there are more n's in the denominator. Let me show you why again. So I have n minus 1, and then once I get to n minus 2, everything below that will be divided out. So I have n minus 2 and down, n minus 2 and down will divide out. So this is the same thing as 1 over n times n minus 1. And the limit, as this sequence goes out forever, right, we're thinking about putting infinity in for my n's. That is 1 over infinity squared, which is just a very, very small number. So that one goes to 0. All right, this one, cosine of pi n over n squared. This is technically a squeeze theorem one, but really you're not going to have to show it with the squeeze theorem. Think about cosine. Cosine stays between -1 and 1. So if that's the case, and I am going out forever, once I write my limit as n approaches infinity of a sub n. So I have some number between -1 and 1 over infinity, over a ginormous number. Doesn't matter what number that is between -1 and 1. If it is over infinity, that is going to go to 0. That's it. If you need the technical squeeze theorem type stuff, right, -1 is our lowest, and cosine of pi n over n squared will stay somewhere between that and 1 over n squared. The limit as this goes to infinity is 0. The limit as this goes to infinity is 0. So since both sides go to 0, the interior function must also go to 0 as well. That is the squeeze theorem. It's squeezing those two to 0. All right. With this one, don't forget about your horizontal asymptote rules. It is the easiest way to do this one. If you recognize the highest power in the numerator and denominator, then your limit will approach the horizontal asymptote, which is 5/3 for that rational function. All right. And one thing that I haven't mentioned yet, I'm sorry, but n is, like we were talking about with the terms, right? Notice the terms, stop it. The terms were a sub 1, a sub 2, a sub 3. I have to have integers. N is an integer. and we're going to stay usually positive integers. I don't really see many that go like backwards. But just keep that in mind as we're doing this. I'm sorry I didn't mention in the beginning. Okay, but this one in particular, right? So if I have -1 to the n, if I think about what that does as it goes out to infinity, right? This is what I'm going to be stating. But -1 to the n, if n is an odd number, like -1 to the first power, or -1 to the third power, -1 to the fifth power, so on and so forth, right? Then it will come out negative. N is an even power, you have -1 squared, which will come out a positive number. So with these, as they go out forever, I'm going to kind of alternate, so on and so forth. And as they go out forever, since the powers here are the same, n to the first, 2 divided by 2 is 1, so this will alternate between 1 and -1 as it goes to infinity. So since this is the case, I can't necessarily say that it goes to a specific number. So a question was asked about, do I say diverge or fails to converge? Diverge is good enough. Fails to converge, I think it's the same thing, but technically I said diverge goes to infinity. But really, if it's divergent if we can't tell where it's going to. This isn't going to a specific number. This is like we would think it goes to 1 and then it goes away. It goes to -1. And we're like, oh, maybe it's -1. We're like, no, it's just back at 1. It's like trying to catch a pot of gold or something. I don't know. It just always goes away. What does it always go away? Okay. That it? That it? That's it. Monkey! Monkey, big monkey! Yay. You did it. All right, as always, please let me know what questions you guys have, and I will see y'all in class soon. All right, bye.